Hi, welcome back. We have 7 weeks left. Crazy. Just crazy. We're gonna get as far as we can. We're gonna, bless you, we're gonna get pretty good in here. We're gonna get pretty good and far. So right now we have a web work up, is this correct? There's a web work on linear algebra that is still open? Am I in the right room? Because no one seems to be responding to these questions. Okay, thank you. Okay, all right, just want to make sure.
That's what I saw before.
It says closed?
It closed yesterday.
Oh, do we need it open more? Yeah, okay, well then we can fix that. That's what I want to know. Is there anything, and did anyone have questions on that thing? And I'll open it back up. Sophia, my friend, would you send me just an email that just says title, just the web work in the title, and I'll get that taken care of. And I'll open it up through Wednesday, end of the day. Would that be good? Does that work? Yeah, sweet. If you need more, let me know. It's easy enough. Takes nothing more than a flip of a switch. Cool. Well, let's get going. We're not going to do this because I've been sluggardly. But what I would kind of like you to do is warm up with a little eigenvalue problem. So I made some special ones. I brewed these up just for you all. And what I would love for you to do for me is to just find the eigenvalues of this. So find eigenvalues, and we'll call that A. Please. And then if you're like, you got that done really fast, how about the eigenvectors? And there's probably a few things that you're going to run into that we might need to talk about. That's my hope. Oh, this is a good warm-up. I hear pages flipping. Nice. Just what I wanted. Run to the restroom. I'll be right back. If you get all that done, I would ask you, what is this doing in the plane? What does this do to the vectors in the plane? If we view it as a transformation of the plane, what is happening? A little bit of refresher stuff up here, just in case you are this looking good? Are we falling into this rhythm? Sweet, sweet. Good work if you are. Could someone help us out on solving this equation down here? Plus or minus I. You're not even in complex analysis or modern geometry. Fantastic. So this one here has imaginary eigenvalues, pure imaginaries. And the way to see that would be a couple routes. You could use the quadratic formula, or you could, since there's no lambda term, just move to this form and then take your square roots. Since you're taking them, you gotta put a plus or a minus. Square root of -1 is literally the definition of the number I. Is anyone not familiar with I? Because that's cool, I could talk about it gladly. Everybody feel cool with imaginary number I? Okay, cool. So our eigenvalues are plus or minus I. That's something we can't picture really. Did anybody find, well, there's a way to picture it, but not in the real plane that we deal with. Did anyone find the eigenvectors for this? Not yet? Let's take a minute and try to find those. I would say either work on that or work on what is this doing in the plane if I take a vector. So take one of these two problems. If you take a vector in the plane, x, y, what is happening to it? If we transform it with that matrix. That's kind of cool. We haven't really seen this yet, what's happening here. So it's not a stretching. There's no stretching involved here like we were talking about, no dilation. I need like blinders, so I stopped looking at Cecil's pastry on the table there. It looks really good. Oh, that's good. That looks good. Yeah. So, yeah, so we subtracted this guy.
That came from doing the wrong thing.
Okay, got it. That would do it, because that's totally right for that thing up there. I agree.
Mm-hmm.
Yeah, it gets a little weirder now.
Yeah.
Is this making sense? How?
Yeah.
What happened? Okay, awesome. That looks good, what you got going on there. Yeah. Now you can just pick any value you want for x or y, and then find what the other should be. Because those two equations are consistent, right? They're the same.
Yeah.
So just pick a value for x,
Okay.
you know, like 1. Any non-zero value will be great. putting, if you've had linear algebra, I'm just putting some other descriptions of what we're doing up here that will resonate with what you've learned in that class, and if not, don't worry about it. If these things seem obscure or incomprehensible. Up kind of just a new outline. This will be, in the recording, just a different way to say what we did last time. But these eigenvalues, being able to do the stuff we're doing here is really essential to the next month of our class. So let's see, so is it x equal to 1? So for lambda equals I, you want a vector that is a multiple of this one here. And that could look all sorts of different ways. So I'm curious if someone got a different vector for corresponding to the eigenvalue I, which is just weird. And then this vector is another weird, this is even weirder because it's a two-dimensional thing with this weird imaginary component. Eventually that will make sense to us. Right now we're just doing it just for practice, but we'll make sense of that pretty shortly. Can I help anybody? Does anybody have any confusion about getting to here? Did anybody get a different answer? Because you could. There's like infinitely many ways this could have gone. You could have instead of setting y, so here in this, so a couple of notes. When you get to this point, these equations should say the same thing. If they don't, something got screwed up. So these should just be repeated information because we actually want infinitely many solutions here. We don't want two equations that narrow things down to a point. We want two equations that describe a single line in space somewhere. So do you see how these are the same? Could somebody explain to us how these are the same? Because they look super different. How could I move from the top one to the bottom one? Lou?
Wait a minute.
That's all good. It's all good.
So I was originally gonna subtract the y in the first equation.
So like move it like that?
Yeah,
Okay.
and then I was gonna divide, but then that would not work.
Well, I wouldn't say it wouldn't work. Divide by I?
Yeah.
Yeah, let's do that, sure. But let's just keep the y on the same side, right? But I like that move. So let's do this. And since this one has a negative x in front of it, I want to get rid of that I. So that's a good move. So I'm just gonna divide through here by I. And so this thing becomes negative x, but then I've got y over I equals 0. Can somebody, maybe one of my students in modern geometry, tell me how this becomes that? Because it looks pretty close. Doesn't have to be modern geo people either. Oh, yeah.
Couldn't we have just multiplied by I? The first equation?
Yeah, we would need to multiply by minus I, but we could have done that too. Yeah, absolutely. We're going Lou's route. Your route, absolutely just as good. Can you help me out with this one here? Like how this is actually that?
Oh.
Yeah.
Because negative 1 over I is equal to negative I.
Beautiful. That's lovely. Yeah, absolutely. So in this one here, think about what 1 over I is. Well, we know that I squared is negative 1. So if I take this and manipulate it, let's divide both sides by I. And this is what Voyn just literally said for us. So now multiply both sides by negative 1. And we get 1 over I is negative I. So this 1 over I just becomes a negative I times y. So those two turn into the same thing. Good stuff. Cool. Everybody cool with that? I mean, as cool as you can be with it. It's weird.
Yeah, I have a stupid question. But for
No,
the
you
trace,
don't.
it's negative b plus c, right? So why is it not negative 2?
Wait, so, the trace is,
Oh,
trace is the downward right diagonal sum. Is that what you're asking, Tracy?
it is? It's not bc?
It is not.
Oh. Okay, I got that super wrong.
Good thing to note, for sure, because you'll get a lot of wrong answers with that trace. Yeah. Thank you for asking. That's not a dumb question. It's important. Is that helping?
Yeah.
Okay, awesome. Any other questions here? Oh, groovy. Yeah, Lou.
So will I be like pretty relevant to really understand like for the rest of the semester?
No.
So it's just like understanding like this process.
Yeah, and basically, I'll tell you what's going to happen is we're gonna like at some point get these imaginary eigenvectors, and what we're gonna do is convert them into something that doesn't even look like it has I in it. We're gonna tuck it under the covers and just like lay on top of the bed. And it's gonna be great. Yeah, exactly. It's gonna be really chill. Yeah, it's like, what are those lumps? Stop thinking about the lumps. Just scoot over. Okay, and then if you wanted to check lambda equals minus I corresponds to the eigenvector 1 minus I. We could work that through and get that. Has anybody, so like this is stuff we'll worry about a little later. It was just good practice, and I wanted to introduce I today because it's going to pop up a little bit. What does this do to the plane? Anybody help me with that? Yeah.
It rotates it?
It rotates the plane. That's really what I want to talk about today, that imaginary eigenvalues indicate a rotational motion in the plane. Let's see that. How did you see it, Lou?
Well, I said like, I was looking at it and I said, if I had the vector like 1, 1, when you just multiply it with the original matrix, you end up getting, I want to say like 1, negative 1.
Yeah.
And I was like, okay, that looks like a rotation. So then I tried something easier even still and did like 1, 0, and it just throws it right down.
Did like a basis vector.
Yeah.
Yeah, nice. Cool, this is a great one. So pick any vector in the plane, see what happens. So if we take this one, it's going to be the dot product of that vector with that vector. So it's 0 times 1 plus 1 times 1. dot product of this row with that vector, -1 plus 0. So we get this, and then you want to plot that out so you get a nice visual in your mind. Here's 1, 1, and then 1 minus 1 is that critter right there. And so it looks like what we got is a rotation by 90 degrees. And I can do that with any vector. So like Lou said, well, I checked a simpler one. If you took the vector 0, 1, what would that do? I'm getting scared. Hold on. So let's see here. Did I do that? Okay, let's just do it. So 0, 1. Oh yeah, everything's cool. Thank goodness. When I multiply these two, take that dot product of those two, you get 1. Take the dot product of those two, you get 0. So this vector ends up right there. So it just rotates as well. Yeah. Takeaway. Complex eigenvalues, anything that involves I means there's rotation in the plane. That's all I really want you to know right now is that complex, so complex is this, you have a real part and an imaginary part. But the minute you see this, I indicates rotation. And to figure out what the rotation is, real. Okay, there we go.
Rotot?
What? Yeah. Tater tot, rotator tot, indicates rotation. That's all I need you to know for today. Cool. So let's look at an example. Let's do an example together. I want to bring in an application because this stuff is fun and beautiful, but it's really powerful for understanding physics and, dare I say, love affairs. I'm going to show you a couple of models today. And one of my favorite things, it's not in our book, and that's not even a book that I pointed to. One of my favorite things to do is use systems of differential equations to model a relationship between two peoples, critters, whatevers, and then predict their relationship and watch it unfold. And it's just a freaking awesome thing to do with math. Complete bullshit, but glimmers of truth emerge. You're like, I know that person. The codependent person, I know that person. Maybe that person's in the mirror. Who knows? So let's do a quick couple applications. Applications of systems of differential equations. So we're going to do applications. We're going to look at a few applications. I'm going to set up some stuff for us to use when we actually start solving differential equations. So we'll just refer back to these things. But one of the things I haven't shown you yet is one of my favorite physics things. It's a mass spring system. Very simple mass spring systems, but really fundamental to understanding diffie-Q. And one of the classic examples. So let's start. I've got a spring hanging from a block of wood or something. Just a spring hanging straight down. Spring's just there, there's nothing on it. That's just the spring. So here we have, and I'm going to be even more precise, it's a linear spring. What do I mean by linear spring? Can say, hey, physics people. I got some heads looking up. What's a linear spring? What do I mean?
It is only dependent on gravity and the spring constant, not like any angles.
Yeah, that's pretty damn right on. Let's see if Katrina, you were saying something. I think maybe not. Okay, I thought I saw your mouth moving.
No.
Something. Okay, cool. That's good. I like that. So, do you know Hooke's law?
spring constant length, right? Something.
So it's, yeah, that's, yeah.
It's like
yeah.
negative
What's that?
Negative kx.
Oh,
Oh shit, yeah, that's good stuff.
yeah, negative kx.
Yeah. Okay, yeah, more, yeah, and then
More.
we're gonna use kx, we're gonna assume k is a positive, yeah, here, you guys, you got it. Oh, awesome, thank you. So, Hooke's law is for a linear spring. And what this means is that if I have this spring and I want to extend it by x units, the amount of force required to do that is linearly proportional to the extension that I want to produce. So in other words, Hooke's law says this, that the force is k times x. So this is the force required, and this thing here is the spring constant. And this is, so good job remembering that kx, that's awesome, makes me very happy. Spring constant. This basically is the strength of the spring. If k is large, it's a very stiff spring. Like a, like a shock absorber or something like that. If k is small, and let's make sure, let's just get this out of the way, k is a positive number for us. K is small equals a loose spring. Just kind of flopping around, just bounces all over. So this is the force required to extend the spring from its natural position x units. So this is the extension on the spring. We're going to work with that. And this is true for most springs. If x is tiny, when you get a spring and you really stretch it, things become nonlinear in almost every spring. So this is an idealized spring, but it works for small x with almost any spring as an approximation of the force required. So we got a linear spring. Cool. I got it. That guy's just hanging over there. I kind of want to have a little series of things. I'm going to take my spring, governed by that Hooke's law, and I'm going to hook a mass onto the end. So I'm going to take that spring and attach, and so it's going to stretch a little bit, a mass m. So m is literally the mass of the thing that I put on the bottom. And you can come up with what the mass of the attachment. Cool. So when I put this weight on here, it's going to pull the spring down a little. Let's start getting some coordinates in here. Let's say that when I attach that mass, it stretches the spring L units. Why did it stretch the spring at all?
Gravity.
Yo, exactly, gravity. So gravity is the reason this mass moves toward the Earth right down here. The force exerted by a mass m is what? What is gravity? What force does gravity exert?
Negative force. Or a negative.
What's the formula? So how would you figure the force? mg, right? Yeah. So let's write up a couple. This is, isn't this Newton's second law of motion or something like that? That force is mass times acceleration. Yeah. So if you want to take a mass m and make it accelerate at a certain rate, this is how you figure out what force is applied, or what force was applied if I already know it's accelerating at a certain rate. So that's Newton's second law of something. I don't know what. Some kind of second law. Some kind of second law. So the force exerted here, so now, right now we have a downward force mg, thanks to Newton's law. And g here, if we're using meters and seconds, kms, it's 9.8 meters per second squared, or 32 feet per second squared if you're like building Noah's Ark or something like that. You know, like 14 cubits per whatever. So that force is pulling that thing down. And the spring is there responding in its own way. So once I set this and that mass stops, we are at equilibrium right now. The spring is pulling up with a restoring force given by Hooke's law. So the force pulling up is the extension times K. So KL equals the restoring force. And then these two things, KL is equal to mg at equilibrium. Is this all sounding right? Reasonable? Good story? Great story. Love this story. Okay, cool. Well, that's a pretty boring mass spring system. There's just the spring floating in the air, not moving. So we're gonna move it. I'm gonna pick this screen, I'm gonna touch this mass, and I'm gonna pull it down a little bit and stretch that spring, and then I'm gonna release it. And what will happen? You're gonna start going up and down, right? Yeah, just gonna bounce it, it's gonna start going up and down. So let's move that spring first. So now, extend the mass, x units downward. And we're gonna set up a coordinate system here that means x is positive for downward extension. And you can think of this as x represents extension. Let's actually write that. Extension. And so x is positive when the spring moves, when the mass moves down toward Earth. And x will be negative when I have compression above the equilibrium state. So when I pull it down, x is going to be positive, and then when it comes back, here x is 0, no extension, and then x becomes negative when we're compressing the spring upward. So here, and then x is less than 0 when we have compression. So it's a little bit weird because we're used to positive being up and negative being down. This is going to be the complete reverse of what we're used to and what our brains have been trained to do. So let's draw a picture as to where we're at. Okay, so now the spring is stretched a little bit more. Oh shit, I should just put him over here. So because I've got all my little things set up here, my little drawing. So now I'm going to extend it down. That is supposed to represent a spring. So right now, this is equilibrium, that line. That's where it rests without any motion. This distance here is x, the distance to the center of mass of that weight at the bottom. All right. So now we're going to go to Newton's second law again, get this all figured out, because what's happening here is I've applied a force to this system and it's changed things, but some things always remain true, and one of those is Newton's second law. So let's go back to Newton's second law, which says mass times acceleration equals force. If x is my position, what is the acceleration of x? So what's the velocity, first off? So if x equals position at time t, let me help a little. Let's put some extra variable. Position at time t, extension at time t. What is the velocity?
The derivative.
So first derivative. So that equals the velocity. And then what's the acceleration, Lou?
The second derivative.
Hell yes. X double dot, yeah. X double dot is the acceleration. So I've introduced some force into the system. I expect an acceleration of that system to result. So this guy here, the acceleration, is x double dot. Uh-oh, getting some equations. Now we just have to look at the cumulative forces acting on the mass. On the system. So what is going on here? Well, I've got the spring force pulling me up. When I'm down, spring force is acting in the opposite direction. When I'm up, when x is positive, the spring force is acting in the negative direction. When the spring is compressed and x is negative, the spring is pushing downward in the other way. So over here, the restoring force of the spring is acting opposite the acceleration. Let me stop. There's more that's going to come in here, but I want to stop right there. I better take a look at my little notey poos here. Oh, wait, that's not the full extension because, sorry, that's what I'm missing. Okay, the full extension of the spring, you also have its original extension, L, because L was where we started. That's the natural length of the spring with the weight on it. And hold on, shit, sorry. So it's gonna be negative K, I'm screwing this all up, and then X, the extension, plus L, that original extension. There we go. Let me stop, because I kind of fucked that up. I've been doing so good, like I haven't cussed all day. I felt like I haven't cussed in a long time, and then this happened. What other force is acting here? So this is all spring stuff. This is the spring force. What else is happening still that I haven't accounted for? Gravity. Gravity is acting this way, which we're saying is a positive direction. It is acting in the same direction as x. So we're going to add mg on. And now we've got the whole system modeled. But some cool stuff is going to happen. This looks terrible. Let's actually do a little math here. So it's negative kx minus kl plus mg. Anything cool happen? Because I know one thing that I haven't used. And I would love for this equation to be more elegant. What do we need here? Or what can I do here? Something goes away.
We cancel the masses.
Well, I could if there was an M here, yeah, I could totally do that, but there's no M here, unfortunately. But that's pretty close to the idea. Let me give a hint. Why?
Cancel those out
How come?
because that's equal at equilibrium.
Exactly. At equilibrium state, we knew this was true. KL equals mg. Here's minus KL plus mg, so this equals 0 because KL equals mg. And holy smokes, we've got something beautiful now. We've got a differential equation, a kind we've never seen. It's actually a second order equation. So we've got mx double dot. I'm going to move the kx to the other side and get this. So this, bless you, is the basic spring motion equation. So this is a second order because it's got a second derivative in it. We've never seen this yet. We're going to actually rewrite it as a not second derivative using systems. So here there's two derivatives. To get rid of two derivatives, we have to actually just add another dimension. So we pass kind of one of the derivatives to another dimension, and we have a two-dimensional system that only involves a first derivative. Now that's not obvious yet. It wasn't obvious to me for a long time. I'm going to hope to make it obvious to you today. So this is the second order differential equation governing the mass spring system. Now, the one thing I haven't talked about here is that there's no friction. This is completely bogus because that system doesn't account for the drag of air that's going to happen and just entropy in general. This thing's going to die out, energy's going to dissipate because you know that a spring really goes like that, right? They stop oscillating eventually. They don't just keep going forever. So here we are assuming no friction. We'll add friction a little later on, not today. If I add friction in here, friction ends up being proportional to the velocity. And we'll toss that in. And the way to think of that is imagine yourself walking through a deep pool. So you've got a pool of water and it's up to your chest and you're trying to walk through it. And everybody's probably done this, walked in some water. You can, if you walk slow, it's pretty chill. You just kind of just walk and walk. And as soon as you try to go faster, you feel the push. The faster you try to run in water, the more it pushes. So the force that you're getting back is proportional to your velocity. We'll do that later. Okay. So that will become a friend of ours at the end of the semester when we come back to higher order diffie-Qs. But that ain't what we're talking about today. So let's convert this into a system of equations, differential equations. Here's how we're going to do it. I'm going to go and introduce the velocity anyway. So let the velocity, x dot, be denoted by a new variable. So I'm going to introduce this new variable. Introduce new variable, v, which equals the velocity of the mass. Go, yeah. Then take this guy here. What is v dot? Well, v dot, the derivative of the velocity, is the acceleration, right? And I actually know how to turn the acceleration back into the state, the position x, with this equation. So this guy here, I'm going to introduce, and notice that x double dot can be replaced with negative k over mx. Just take this thing and solve for x double dot. So this equation here is going to become v dot equals negative k over mx. And look at what we got, my friends. We have a system. And it's in two variables, in x and v, position and velocity. And we have x dot equals v, and v dot equals negative k over mx. And if I did this in a matrix form, holy smokes, let's do that. So in matrix form, this is position velocity vector dotted. So this means take the derivative of each of these things. I'm just trying to express this thing here as a single thing, equals, what is the matrix going to look like? What's the matrix look like? Can somebody help me out who hasn't helped me out today? That would be cool. What goes in the top row so that we get x dot equals v? I want that dotted with that to just be v. Help me out here.
0, 1.
0, 1. Beautiful. If I put a 0, 1 here, that dotted with that is v. How about, was that Cormac, was that you? Yeah, can you help me out with the bottom 1, 2, friend? So we get that guy.
Negative k over m0.
Love it. Cool. Now we have a system of differential equations that expresses the motion of a mass spring system in a whole different way. it relates the position and the velocity of the system, as opposed to the original one that we had that was acceleration and position. How's this sound? I don't expect you to regurgitate this at any point ever. Just want this to make sense today. Can you do me a favor and find the eigenvalues of that matrix? And remember that K and M are both positive quantities. Don't worry about, don't do the vectors. That not particularly important to us. Characteristic polynomial looking good? Yeah. Tara, what'd you get for your eigenvalues?
I had plus or minus I times the square root of k over.
That's lovely. Yeah, let's take a look at that. So you can take this thing, you can quadratic formula it, but easiest way is to just move that constant to the other side, like so. And remember that K and M are both positive quantities, so this is a negative number over here. And so when I take the square root, it involves an imaginary. So when I take the square root, lambda equals plus or minus square root of negative K over M. I'm going to show you how to do this. This is plus or minus square root of negative 1 times K over M. That's plus or minus square root of negative 1, square root of K over M. And that's I. So those are my eigenvalues. Any questions on that? So they're imaginary. What does that mean in the plane? What kind of motion is happening in the plane? Rotational motion. So this indicates, so since these are imaginary, since evals are imaginary, we have rotation in the plane. Now we don't quite really know what this means in terms of a differential equation yet. That's actually going to be like Wednesday and next week, and we're going to get into that. But we do know that it means rotation. And in fact, let me just give you a cool example here to see this. I'm going to take this guy down here. So we have this thing here equals this, just to give you a little intuition about what's coming and why it works. And let's look at a very strange way to represent a system. Horizontal axis is the position, the extension of the spring. V is the velocity. So let's say the position was at 1, 0. So this point right here, let's say that's 1, 0 or 1, 0. What is my velocity? What is that vector going to be? So at x equals 1, v equals 0. So think about what that means. Extension of 1, velocity 0. It's not moving at that instant. It's extended 1 unit down, and it's not moving at that instant. This is zero velocity. Oh, I thought you were doing some kind of sign. I thought you were like indicating some kind of physics sign language to me or something. Demented man. So what we get here is that x dot, the velocity, is what? At this point, what is my x dot? 0. Which makes sense, right? Because I just literally said the velocity is 0. So what Lou is doing is plugging that in here, doing that dot product. And then the second one, the velocity, v dot, the acceleration is going to be negative km. And so v dot equals negative k over m. Well, that's the acceleration. So the acceleration is negative k over m. So what is probably happening here is that, I can probably show it best this way with some sort of goofy demo. We got my spring. Here's equilibrium. Spring's doing this. Where we are right at that moment is we have an extension of 1 and a velocity of 0. We've reached the maximum point that the spring can go. It's stopped and it's getting ready to turn around with acceleration that's negative, pulling it back up in the negative direction. So full extension, full acceleration at that moment, coming right back up. If I were to plot out in this chart here, this graph, what the trajectory looked like, it would look like this. Let's see, wait, so we are, v dot is negative, so it would go like this. Let's think about this. Let's think about what this picture is telling us, because it's kind of profound, and there's a lot of information in here. This is the place where we started. So here we're at full extension. Where am I at here? At this point, what is the spring doing? Can somebody tell us? What is the spring doing at that point? Yeah, boy.
It reached either the top or the bottom. At that point, it's the top.
No, so here, actually here, x is 0, so we're at equilibrium. Does that make sense? So so the spring here, it fully extended right here. Here, okay, I'm gonna move the spring. Here's equilibrium, right here, this bar. Here's where we're at right here. Here's what's happening. Right at this moment, I've crossed equilibrium. And I have maximum velocity. I've achieved maximum velocity in the negative direction, upwards. And then it starts to slow down as I move up to maximum compression. So right here at x equals -1, I'm at max compression. And now it's going to start moving in the other direction. So notice x is decreasing, velocity is increasing. The mass is at its greatest velocity right at equilibrium. And then it starts to slow down because the spring's pulling back. And then the spring pulls it back, it speeds up. And then it starts to compress. So the spring is like saying, slow down, slow down, slow down. And it stops. And now then the gravity starts pulling and the spring starts pushing. And it speeds up and it's max velocity slowing down. And it's all expressed right there. It's just a very difficult thing to look at and to comprehend in many ways. So we will come back to this. Y'all look totally jazzed right now. I don't know how I could exceed this except by talking about people hooking up. So let's do that. PG version, not G version. Let's do another example here. So that's one example. This is my favorite, like I said. Example, relationships. So we've got two people involved in a relationship, R and J. And those can be any peoples you want. Rob and Jeff, Robin and Janet, or just whoever you want, any combination. You get a hetero combination in there too, whatever, doesn't fucking matter. Two people involved in a relationship, Romeo and Juliet. Where the RJ come from. So this, we're gonna make this a function of t, because we want to eventually understand this relationship over time and what happens to these people as they couple and perhaps decouple. So this is equal to R's love, hate for J at time t. So R positive means that's love for J, and R negative is not love, the opposite, disdain for J. Similarly, J at time t is J's love-hate for R at time t. In the same way, positive means J is head over heels. The more positive that value is, the deeper in love. The more negative, the deeper in disdain and dislike. And get the fuck out of my face. I've had enough R for today. So, we are going to model them as a linear system. We're going to say that the rate of change in R's love for J. This is hard to think. It's like a hard thing to put in your head. This is the velocity of love. And I coined that term. And then Eric Fretz wrote a song about it. You know, if you know Dr. Fretz. Yeah. So this is the velocity of R's love for J. If R is positive, if R dot is positive, that means growing love, growing more in love, deeper in love. Love. This is losing it. Losing that love and feeling. Not that they still could be in love. It's just getting old. We need a break. Please go get some friends. Just getting a little close in here. So,
Speaking from experience?
perhaps, R dot, J dot. I mean, I've been married 3 times. I have a sense about this. So, R dot is going to be a combination. So the velocity of R's love is a constant times R plus a constant times J. So the velocity of R's love is a combination of their current states of love. Does that make sense? Yeah? And we don't know what A and B are, and these A's and B's determine R's personality in this relationship. So whatever those parameters are, we can set them to create a different person in this relationship. And then down here, same thing for J. Their velocity of love is a combination of their current states in some way. So here A, B, C, and D are constants. So let's look at a few relationships and see if we can put a name to them, because this is where it gets fun. We're not going to be able to solve these today. We got to do some more work first, but we'll get there. So let's take a look at this couple example relationships. R dot equals J, J dot equals R. You take a minute. What kind of people are these? What does this relationship look like? And it's going to take a little bit of thought. And can you come up with a pithy term to describe this couple? We all know couples that are troubled or great or just bland, nobody gives a shit, whatever. What kind of couple we got here? Think of this as velocity of love. Velocity of R's love is equal to J's current love.
It's healthy.
Explain more. Ooh, that's interesting. Let's go. Cool. Yeah. Explain. Tell me more, Trayson.
I think they're both growing positively. I think. Or
If they're already positive, yeah. So let's make a little love plane here. You know. So if they're both in love in some degree or another, this looks like they're both in the same amount of love. Let's actually. R kind of loves J more than J loves R. Yeah. But you're right, R dot is positive. So here we have R is positive and J is positive. So R's love is growing and J's love is growing. Yeah. And that means they're just falling deeper and deeper into love. And that, I guess that could be healthy. Could be a little toxic and dangerous. Like, this is where someone else has to come in and say, you two need friends. Nobody can stand to be around you anymore. But that's, I don't know. So I like that. Healthy seems good. Yeah. Healthy to a point. But is that the only? Can they only keep falling deeper in love? Is that the only possible thing? What if they're here? What is that saying? What's going on here?
As one loves each other, the other.
Yeah.
The
So
other, like.
So who loves who?
It's like this kind of thing.
R loves J.
No.
J loves R.
No, that's right.
Yeah. J loves. So this is J loves R. What does R feel? Get away. Yeah, so R hates J. But somehow they're still together. I think we've all seen this at some point. Yeah, we've been this at some point. We've engaged with humanity in any way. It doesn't even have to be lovers. It could just be parents, kids, siblings, whatever, friends. It doesn't all have to be about hooking up. What about, where are they moving? What is happening to that relationship? Falling apart. Yeah, so say more, Boyd.
I mean, they're going in different directions. So.
Yeah, so since J is positive, J loves R. So that actually, our response to that is like, this person really loves me. I think I love them because they love me. That's not healthy, right? Does this make sense? That right here, J loves R, so R dot is positive. R is growing more in love with J. But what's happening to J? Losing love. J's losing it. It's like, ugh, boy, really, it's getting clingy. It's getting kind of clingy. This is freaking me out a little bit. I thought everything was okay. So, no, I'm in R. R's already hating him, right? Okay, so what am I doing here? Did I fuck this up? Wait a minute. No, J loves R, so R dot is positive. Okay, cool. So here, I gotta get down here. I'm getting myself confused. So R is in hate. So J's love's diminishing. Yeah. So J is growing less in love. Here. So R, since R is positive in love, J dot is positive, and J is growing more in love. Does that make sense? Is that right?
You got that backwards.
Did I get it backwards? Wait, okay. Oh, because I screwed it up. It's R, right? Wait, no. Hold on. Okay, let's settle down here. Okay, so right here, we have R is negative. So J dot is positive. So J is growing more.
No. J dot is negative.
Is decreasing.
Shit, thank you. Okay, got it. Ah, got it. Okay, cool. That's what I've screwed up. So J dot is negative, so J is falling out of love. Yeah. Cool. With R. Gotta make sure we got one more minute. How could I get a sense of the long-term progression here? And the answer is eigenvalues. Let's just take a quick look at this relationship. So let's just use eigenvalues and see if we can see anything interesting going on here. We've got R dot equals J and J dot equals R. And if I convert this into a matrix, like so, yeah? Does that look okay, RJ here? Okay, cool. I was kind of hoping they were going to be in some vicious cycle. I don't think that's going to happen because here we've got lambda squared plus 0, lambda minus 1 equals 0. I was hoping for imaginary eigenvalues there. We don't have that. We'll take a look at that on Wednesday. So here my eigenvalues are plus or minus 1. And that makes things more complicated. This is a complicated relationship. We'll get to it. We got to talk more about all this shit. So thanks, friends. Thanks for coming. Thanks for playing. Crazy game show. Daniela, would you please hit stop, my friend?
So there is a formula